workshop, for the invitation to the world's small bodies community to participate. This is great. I'm going to talk about a new effort that is being organized between Arizona State University here in the U.S. and Lockheed Martin, a big aerospace company, and GeoShare, which is a smaller aerospace company. And we've formed a consortium. We pronounce it MILO. MILO works just fine as well, but and there's an interesting story on the origin of that name that I could get into later if people want. It's not an acronym. But we've formed a new nonprofit called the MILO Space Science Institute, which is part of Arizona State University, but is a collaboration with Lockheed and GeoShare. So I want to tell you about what MILO is and what we're trying to do with this new nonprofit organization, especially regarding small bodies, because we have some pretty interesting and exciting objectives. We're basically trying to test the hypothesis that a consortium of members can band together, pool resources, and do compelling deep space science for much less than what it would cost any individual organization to do, and can be doing science that isn't getting done. So that's kind of the hypothesis. We're trying to enable affordable access to space because it's a shared cost model. And access is an important part of what we're trying to do. And this includes an enormous component of international collaboration. Many people know that there are something like 60 or more space agencies around the world today. There's been this amazing proliferation, increase in the number of space agencies, countries with space agencies, countries recognizing the importance of space in their day-to-day economy, and that's great. And many of these new agencies, institutions, universities, companies that work with those agencies, of course, are trying to get in on the game. The NASA, ESA, JAXA, et cetera, the big space agencies who offer opportunities for international collaboration on missions, instruments, scientists, et cetera. But the problem, of course, is if you're a new player in this game, or you just don't have much experience in this game, you can't get your proposal or your instrument accepted by the big space agencies because it's so incredibly competitive. And in general, the large space agencies are conservative, and they generally will go with sort of known quantities. So it's very difficult. It's a very competitive environment, and it's very hard to break in. So MILO's idea is to create opportunities for new players as well as existing players to get into the deep space exploration business with affordable access. We're science driven. We want to answer fundamental questions in solar system exploration that come from, for example, the US Planetary Science Decadal Survey, or any of the similar ESA planning documents, others from around the world that have outlined the important questions in planetary science and solar system exploration. We're trying to enable new deep space exploration missions and scientific discovery opportunities. Those of you who had maybe proposed instruments for space missions before, or entire missions before, know how competitive it is. In the US, something like 9 out of every 10 mission or instrument proposals that's sent to NASA are rejected. And 10% success rate is not very good, and those 90% of the other proposals are not bad. It's just incredibly competitive. There's just not enough money to go around to pick them all. So there's plenty of science that remains to be done. It's just not getting done because of resource limitations. So we're trying to work ourselves into that field and enable more opportunities, and opportunities for participation as well. Not just providing hardware and doing operations, but participating. And then one of the goals that we have, MILO is a nonprofit. It's run out of a university where you, of course, have an academic mindset and an educational philosophy associated with the organization. So we want to help provide MILO members with services designed to grow their capacities. Things like principal investigator training, things like certifications for satellite operations or instrument operations, testing for thermal vacuum, those kinds of maybe for students or maybe for early career researchers or others who just want to tap into either the expertise that Lockheed brings to our collaboration or on the engineering side and systems integration side, or the expertise that ASU brings to the collaboration on the science side and operations side. We've been ASU is a Research 1 class university. We've had involvement in a huge number of NASA robotic space missions going back to the 60s. So lots of experience that we're happy to share as part of workforce training and capacity building. So one of the things we've done, and we formed the Institute in 2018, and we identified, we have a science council that consists of scientists from ASU, University of Arizona, Northern Arizona University, and members of the Institute contribute scientists to the Science Council. And working with Lockheed, we did identify 3 initial mission opportunities that we are basically pitching to our members as a sort of a demonstration proof of concept that we can do this. And 2 of them are related to small bodies. So I'm going to focus on 2 of them in particular in this presentation. And we chose these mission opportunities with a variety of constraints. One constraint was that since we have to prove the concept, test this hypothesis that a consortium can come together and run a deep space mission, we wanted to do something relatively quickly. So no missions to the Kuiper Belt that take forever to get out there, it's close to home, asteroids, the moon, Venus, Mars, maybe. So that's was part of our thinking. We also wanted to keep it relatively affordable. And what does relatively affordable mean? Well, for example, a discovery class mission for NASA that a principal investigator can propose will end up with a cost cap somewhere between $500 and $750 million, depending upon the particular year, et cetera. So that's a low cost NASA mission. We're trying to get much lower than that. We're trying to get missions built and operated by a consortium that are tens of millions of dollars to hundreds of millions of dollars class. So still some significant money. We're not talking about toy missions. These are serious engineering efforts with serious safety and mission assurance components that involve Lockheed, with serious science that we're going after that is recognized by decadal surveys and other community consensus as being important. But we think that there are classes of missions that can be done, deep space missions, science focused, that can be done for less than the sort of lowest entry point for those kinds of competitive missions at the NASA level. So close to home, low cost, and then the third requirement was really compelling science. So we wanted to go into these community consensus documents, the publication literature, et cetera, the groups like SBAG and VEXAG and MEPAG and those community assessment groups that NASA runs, similar ones, similar community groups on the ESA side and other space agencies, and identify, here's some really important science questions that just aren't getting done, aren't getting answered because the missions are not getting selected. There's not enough resources. So it's important to point out that we're not trying to compete with ESA or NASA or other space agencies. We're trying to augment, really fill in more opportunities. So the combination of those 3 requirements led us to near-Earth asteroids as prime targets for initial missions, and the moon. So I'll mostly talk about near-Earth asteroids. And who are we targeting? Emerging space agencies that I mentioned, universities and space science, departments and institutes that are doing deep space science, maybe through their national space agency, some of them on their own, through their own funding sources, or their own tapping into their own national funding through other means. Corporations, companies, entrepreneurial companies up and down the supply chain who are providing components, instruments, workforce in the space sector, and of course, philanthropy. But our focus is on those 60 plus space agencies around the world and the universities and institutes that are working with them to try to advance their local space science mission goals. So the first mission that we came up with is called NEOshare, and it's a mission that would launch probably in 2024. And it's focused on studying near-Earth objects. Of course, this audience knows there's a large population, more than 20,000 near-Earth objects now identified. A couple of thousand, 10% or so of that population has potential implications for Earth, include the potentially hazardous objects. So there's not only intrinsic science having to do with small bodies here, but planetary defense issues. But of course, and this audience knows, only 5 of them have been visited by space missions. So we have a very, very tiny percentage of the population and the diversity of this population that's been sampled closely enough to get detailed information about their geology, their chemistry, composition, internal structure, etc., to truly assess their individual properties or how they represent the class of objects that they represent. So there's a lot of opportunity here and many, many objects, and very few studied up close so far. So we're trying to address that particular topic of really increasing dramatically the number of spacecraft encounters up close with members of the small body population. So, have we really truly sampled the diversity of near-Earth objects with spacecraft observations? Here's the 5. Eros, Itokawa, Tutatis, Ryugu, and Bennu. And some of these missions are still going. The near mission to Eros was back at the turn of the 21st century. So there's 20 years or more of study of these objects, and we've learned a lot, of course. But it's a good question. It's the right question. Have we sampled the diversity of that 20,000 plus population? This is just another view of these same objects, but shown to their actual relative sizes. So we certainly have sampled some aspect of their diversity, just size, for example, Eros being a large near-Earth object, all the way down to tiny little Itokawa and Bennu. But there are other ways to look at this population, of course, thinking about their surface composition, their colors, their spectral properties. And this is just a summary of the alphabet soup, if you will, of taxonomic types of near-Earth asteroids and their possible associated meteorite types. We don't know for certain on a lot of these asteroid to meteorite connections, but we have sampled some of them, right? The carbonaceous class with, of course, the ongoing investigation by Hayabusa 2 and OSIRIS-REx, sampling those kinds of objects and literally sampling them, and we'll hopefully get some of those samples back to Earth relatively soon. And then the S-types through NEAR and other missions, looking at one of the most common classes and making the connection between that class of meteorites and ordinary chondrites through comparison with telescopic data. So yeah, we are starting to sample the diversity of the spectral diversity, the compositional diversity of this population, excuse me, sorry. But you can see there's lots of this table that's still not filled in. So plenty of diversity left to sample. And, typically we'll go through this process with telescopic observations, looking at magnitudes, looking at colors, doing astrometry, trying to see if we can get objects close enough to illuminate with radar systems like Arecibo, estimating sizes from albedos, visible and thermal observations, et cetera, and telescopically, of course, trying to get to some fundamental characteristics: rotation, state, shape, orbital characteristics, size, mass, density, fundamental physical parameters. So this is really where we want to get to with this population, both for scientific purposes and planetary defense purposes. And all of these are arguably, maybe we can argue, but all of these can be determined much more accurately from flyby or rendezvous missions. Even fast flybys can give us enormous amounts of information in detail about the physical properties, thermophysical properties, intrinsic bulk properties of the small body population. So the idea is NEOshare is a dedicated small vehicle launch that sends 6 Smallsats or CubeSat class spacecraft in a single launch to each perform close flybys of a diverse set of near-Earth asteroids. And we'd launch this mission nominally in 2024, but we have launch dates that extend beyond that as well, reaching the first asteroid just a few months later and the last asteroid maybe 3 to 5 years later. So again, keeping it all relatively contained. All the flybys are happening relatively close to the Earth, so we have high communication rates and not a long time to conduct the mission. Each of the spacecraft is equipped with its own prop system, as CubeSats and Smallsats are and can be nowadays. Each of them will fly by a different target, and some of them can fly by multiple targets. And so our goal is sort of 8 to 10 different new near-Earth asteroid, near-Earth object flybys in a single mission. So we go from 5 to more than doubling the number of small bodies that we've flown past, and we would not just be randomly flying past members of that 20,000 rich population, but flying past them well-selected ones to sample diversity and many different axes of diversity. A relatively simple mission operations scheme. A dedicated launcher sends these a deployment vehicle into a heliocentric transfer orbit. The CubeSats or the Smallsats are serially deployed from the dispenser, depending upon when they need to be deployed to encounter the objects that have been chosen. And each of them just does a flyby from sort of low delta V, kilometer or so per second, to high delta V, 5, 6, 8 kilometers per second, depending upon the object. And that's a choice that the membership and the Science Council will make. And then multiple encounters are possible from each of the CubeSats. So this is just kind of a graphical way to look at that. Single launch vehicle, 6 Smallsats. Now, that you can imagine the scientific return that we'll get from this mission. And you can also imagine that with that population, we have a lot of flexibility, with 20,000 objects and more being discovered all the time. And it turns out, and Lockheed colleagues who do mission architecture work have done this analysis for us. For a launch on any given day, there are more than 100 asteroids and 20 comets, all in the near-Earth environment, that could be chosen for flybys any day. And that, gives you a lot of choices in terms of sampling diversity in spectral type, diversity in size, diversity in binarity, diversity in location, orbital characteristics, etc. And how will the decisions be made? Well, it's a group decision. The Science Council has picked out some example scenarios that we could run, but it's really up to members and their science representatives and their scientific interests and which parts of the science parameter space do they want to check off. Do we want to visit the first binary near-Earth asteroid? Do we want to visit the first M-type near-Earth asteroid? Do we want to find a near-Earth comet, et cetera? Yes.
You have 10 minutes, including time for
questions.
Okay,
very good, very good. I'll fly through the rest of this. We'll do the kinds of measurements you can imagine with imaging, spectroscopy, et cetera, simple geology, simple surface mineralogy, mass if we can get it, if the objects are big enough, density from the mass and the shape model derived volume and other properties. And so really keeping the instrumentation simple, high heritage, imagers, spectrometers, fields and particles, et cetera. Now, we also asked ourselves, is there a thinner, de-scoped version of that 6 CubeSat mission that we could do if we wanted to just focus on a single near-Earth object? And the answer is yes, and that object is Apophis. Of course, this audience knows a lot about Apophis, about a 400-meter diameter S-type object that will make a crazy close pass by the Earth on Friday, April 13th, 2029. Very rare, unique opportunity to observe a pretty large near-Earth object that could potentially go through some changes of its structure, shape, exterior because of the tidal effects of the Earth. It's getting within 6 Earth radii, so that's exciting. There's opportunities there that we haven't been able to exploit before, and the assumption is that the world space agencies, NASA and others, are going to take advantage of these opportunities, that there will be probably large missions that will be focused on the 2029 flyby, and they'll be really important for science and for understanding this class of potentially hazardous objects. Our goal is to do something before 2029. That's why it's called Apophis Pathfinder. So we launch it early, and we do a precursor flyby of Apophis. And this chart shows the close approaches of Apophis to the Earth over the 2020s and into the 2030s. And you can see that April 2029 flyby 0.0003 AU, that's the one that everybody's excited about. But there's other points in time when just because it's a near-Earth object, the asteroid gets relatively close to the Earth. And so it could be encountered with a flyby vehicle in a not too difficult kind of trajectory. And so our idea is to take just a subset of NEOshare, just 2 small spacecraft, maybe a small sat or a CubeSat and a probe of some kind, and just do an initial flyby and provide the initial reconnaissance data needed to feed into the 2029 missions, especially if any of the 2029 missions are going to plan their orbital rendezvous. They'll want to know some details about mass, density, surface characteristics, etc. So relatively simple precursor scout kind of reconnaissance mission that we think we can do relatively inexpensively. So great science and great planetary defense feeding forward into more detailed missions that'll take advantage of that amazing 2029 opportunity. We also have a lunar science option. I won't go into it in any detail, but there are possibilities for MILO members to participate with Lockheed's commercial lunar payload services lander and for very modest cost, get kilograms of experiment onto the moon in lunar environment in the relatively near future. So that's exciting as well. But really the sort of 1-slide summary is that what we're putting together is a mission by consortium, organization of members who participate in teams to build individual satellite spacecraft or components. And what does it mean to be a member? Membership levels are based on contribution. What does your organization want? Just access to mission data for your scientists? That might be an entry level. Maybe a contribution of a component. You want to build cameras or spectrometers, launch them on a shared satellite that others are building. Maybe you want to develop a complete spacecraft. That's a higher price point. And we think that we can do NEOshare for somewhere between $200 and $250 million. We think we can do Apophis Pathfinder for somewhere between $40 and $50 million. So if we get 10 members, the cost is divided by 10. 20 members, the cost is divided by 20. The details, of course, would have to be worked out in some arrangements of who builds what, who needs what, who wants to develop what capacity. But one of the ideas is to take that competition out. So you just join, like you join ESA, like you join the National Geographic Society. You join, and it costs money to join. The membership fee goes to a central organization that's at Arizona State University. We take a little bit of that membership fee to buy the launch vehicle. We take a little bit of that membership fee to run the operations of the spacecraft. And then most of it actually goes back to members, just like ESA does, for example. Most of it goes back to be spent in country, in institution, on universities, student training, operations, building an instrument, what have you. So it's this very similar kind of model to ESA, but much smaller scale and focused specifically on deep space science. And we're also running a Smallsat accelerator program and that will help members learn more about, help them learn from subject matter experts like Lockheed engineers, like ASU scientists, about how to participate competitively. So they'll grow their capacity and compete with bigger space agencies for more missions. So that's our idea. We welcome more ideas. We welcome mission ideas. We welcome members. More detailed, we can have more detailed conversations. And really, it's what are your organizations, your institutions' deep space science goals that aren't getting met, and how can MILO help you to reach those goals? So that's it. Thank you.